My name is Geneva Bowling, and today I'll be presenting my lab year report on black holes and orbits. The purpose of this experiment is divided into two parts. In part one, we analyze the star's motion around the unknown black hole located at the origin to estimate its mass. In part two, we use the planetary system to simulate trajectory for a spaceship navigating around the planet and its moon without crashing. As a result, I estimate the average mass of the black hole in part 1 to be 7.7 times 10 to the power of 33 kilograms. In part 2, I found a safe, non-crashing trajectory for the spaceship using the initial velocity of negative 625, 0 meters per second. To make our models, we rely on several fundamental ideas. First is Newton's second law, momentum principle, which states that the net force acting on the system is equal to its rate of change of momentum. Because momentum is a vector, its rate of change can be split into parallel component, which changes the object's speed, and the perpendicular component, which changes its direction of motion. Second, we utilize Newton's law of universal gravitational, which describes interactions. The force is directly proportional to the product of interacting masses, inversely proportional to the square of distance vector r separating them, and acts along the unit vector directional line r hat. For part 1, the system is a star and the surrounding is a black hole. The initial conditions are mass is 2 times 10 to the power of 30 kilograms, and the time is 86,400 seconds, or 1 Earth day. For this section, we have our initial conditions, and then we are calculating the star's velocity. For this section, the code calculates the initial and final momentum vectors using P equals mv to determine delta P over delta T. Since F net is dP over dt, we equate them directly. To find the parallel rate of change, we compute the change in the momentum magnitude of momentum over time multiplied by the unit vector p hat. Subtracting this parallel part of the total dP over dt gives us a perpendicular component. By setting the magnitude of F net equal to the gravitational force equation, we algebraically isolate and solve for the unknown black hole mass for every single step. Averaging these values over the entire trajectory yields a final estimate mass to be 7.7 times 10 to the 33 kilograms. And this is our result. As you can see, the orange arrow represents Fnet, the magenta arrow represents parallel component, and the cyan arrow represents the perpendicular component. For part 2, the system is a spaceship and the moon, the surrounding is a planet. Our initial conditions are mass of planet is 6 times 10 to the power of 24 kilograms, mass of moon is 7 times 10 to the 22 power kilograms, mass of spaceship is 7 times 10 to the power of 12 kilograms, and delta T is 60 seconds. And here we have our constants and our initial ship speed and velocity. To predict motion, we calculate the individual gravitational force vectors acting on each system. For the moon, we sum the pull from the planet and the spaceship. For the spaceship, we sum the force from the planet and the moon. These net forces are updated inside the while loop. We then apply the step-by-step velocity update formula, followed by the position update formula to advance both objects step by step. Through trial and error, utilizing the initial velocity of negative 625, 0 meters per second successfully influenced the ship's motion by both massive bodies, creating a complex path without triggering any crash conditions. For possible errors, since this is a simulation, does not always represent reality, and we also use a lot of trial and error to find velocities. How does net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components? Mathematically, net force and the rate of change of momentum are completely equal, according to Newton's second law. However, based on observations, they represent different things. The rate of change of momentum is something we directly observe and measure by tracking changes in the object's position and velocity over time. Net force, on the other hand, is a physical sum of environmental interaction causing that motion, which requires knowing the structural properties like mass and distance. If we wanted to predict the motion of the entire system, what would be needed in your computational model? Well, there's a black hole, the star, the planet, and the moon, which means there are 3 forces times 4 objects, which means there'll be 12 forces acting upon in total. Regarding these interactions, they would not contribute equally. For example, the black hole has the biggest mass compared to all systems, and therefore would have the biggest gravitational pull, whereas the moon or the sun's gravitational pull is so small that it is negligible.